So let's get to the rigorous definitions of these notions. The first thing I just want to get out of get this definition out of the way is where basically we call a system, or you can use the notion of equilibrium point, but let's say the system Lagrange table, if for every initial condition you can find a bound. So that means wherever you start there is a bound that happens, and then it's a very simple notion in that sense. This was originally defined by Lagrange, not quite anything to do with an equilibrium point. In control systems, like I said, in most of the time we want to maintain a particular point, so this is rarely applicable to control systems. So this is not going to be anything interesting in our case, right? Though some of the methods we learn here can be used to show Lagrange stability, but that's not the focus of this particular course. The boundedness of solutions is much more important in stochastic systems, because the examples that we typically find in real world, like queuing theory and things like that, queuing systems and things like that, the notion of equilibrium is more difficult, but being bounded is important, right? In the example of water level control, we saw that basically if there is a perturbation, small leak and things like that, this valve keeps opening and then fills and things like that, and it keeps going back and forth, right? Suppose this leak is actually somewhat persistent. It could be constant, it could be time varying, it could be probably, let's for fun basically, let's imagine that it behaves like a sinusoid wave. The rate of leakage is behaves like a sine function. How would the valve behave, right? It keeps opening and closing, and then always trying to maintain height. And you'll see when the leakage is persistent and this valve is opening and things like that, it may happen that the height that we want to maintain may not be maintained at all, except in an average sense. You will be maintaining around that particular point. And then that brings us to a notion of something called bounded input, bounded output, where if the leak in this particular case, which we call as input technically, is bounded, it's not really nasty or anything, then the output in this particular case is the height. The height will be bounded, right? It may not be exactly equal to the desirable height, but the difference from the desirable height, it's actually going to be bounded. And that notion is very, very important, quite difficult for nonlinear systems to actually prove and things like that, but the notion in linear systems is happens to be equivalent to some of the other notions that we will look at, but in nonlinear systems it becomes a lot more difficult, but this is actually a very important notion. Unfortunately, we won't have a lot of time. If time permits, we may actually look at some theory to show bounded input, bounded output stability, but most of our focus is going to be on equilibrium based stability notions, right? And turns out that if you have equilibrium based stability, then a certain stability will imply bounded input and bounded output stability, and then that's how one can address bounded input, bounded output stability of nonlinear systems, right? Like I said, in linear systems they are equivalent, and so we are happy to use one of the notions, whichever is easier. So that brings us to the notion of equilibrium based stability, and this was I can say single person's work to start with, and then some generalizations happened over the years since this person, but essentially all the ideas that we use in generality also are not too different from what Alexander Mikhailovich Lyapunov proposed back in 1892. There's quite interesting story about his thesis and things like that. His committee involved people like Markov and Chebyshev, who were very well-known mathematicians, and he graduated at the age of 35 or so, from his PhD, late even for those times, mostly because of his teaching responsibilities. Um, but his original work before he started looking into this problem was something to do with perturbations in probability, and he is a celebrated result in probability. He has the most general notion of center limit theorem, for example. Um, so while looking at a lot of these probability issues and things like that, he was also quite interested in mechanics problems, and one of the problems that he wanted to understand or resolve is the so-called multi-body problem, or the three-body problem, and its generalizations, right? So needless to say, he didn't he did in many ways explain chaotic systems through this notion of Lyapunov exponents. So later in life he actually introduced these notions of Lyapunov exponents to describe some kind of degree of chaos and things like that, right? But while trying to solve this, understand the three-body problem and multi-body problem, he came up with this notion of Lyapunov stability. We call it Lyapunov stability, and he called stability of an equilibrium point and things like that, right? So, and as I said, the notions that he introduced back then in 1892, his thesis is quite accessible even today. Which is what we use, right? He not only introduced the definitions, he actually showed how to check those stability notions. So let me perhaps use pen and paper to see what we mean, and then go back and provide a rigorous definition of stability. So let's say this is an equilibrium point, right? And we have seen so far that most of the time, basically, if we perturb from there, so I'm going to, instead of starting at the equilibrium point, by definition, if you start at the equilibrium point, you remain at the equilibrium point. But let's say you start, slightly away from it. What will happen? Well, multiple scenarios are possible. One, you're going off somewhere, infinity. Or you may actually just go very far and then eventually reach this equilibrium point, right? Or it's possible that you may, remain close to the equilibrium point and then converge to the equilibrium point. Sometimes you may not even converge anywhere, you just remain in some orbit close to the equilibrium point, right? So these are the various possibilities, and probably more, but for the time being, we will think of these possibilities. So, loosely speaking, we can think of stability of an equilibrium point as, there are two aspects to it. One is actually, if you perturb, do you remain close to it? The second notion is, can you actually go back to the equilibrium point? And these two notions, let's say, one notion is basically, start close, remain close, right? That's one notion, right? Slowly we will define that as something called Lyapunov stability, or is the basic notion of stability. So it doesn't require us to think basically that the solution is going back to the equilibrium point, right? If you start close, you remain close. It's a nice, well defined behavior, right? The other notion is, of course, wherever you start, converge to the equilibrium point. Okay, so we can call this as asymptotic convergence. Okay, so there are cases where wherever you start in space, you will reach this particular equilibrium point in the asymptotic sense, right? And for that to happen, of course, you need to have only one equilibrium point. You can have multiple equilibria, in which case asymptotic convergence cannot be expected. right? So but if you have one single equilibrium point, you may actually start anywhere and then basically going to that particular equilibrium point, right? But then this may not have this notion of remaining close. You may start very close to this equilibrium point, but you have to before it goes back to the equilibrium point, it may actually go out all the way, I don't know, 100 kilometers and then go back and then converge to this thing. So in that sense, these two notions, start close and asymptotic convergence, are independent. I mean, there are examples where only one of these things will happen, right? Although many examples, and those are the interesting examples where both of them happen simultaneously. And in fact, when both of them happen, basically we call that as asymptotic stability, right? Let me list down the two notions. The first one is called Lyapunov stability, and the second one is asymptotic stability, right? So perhaps we can think of a couple of examples. Let's say x dot is equal to 0. So what kind of clearly 0 is an equilibrium point. If you start at 0, and you'll remain at 0. So is every other point. That's a different thing, but 0 is certainly an equilibrium point. So can this 0 solution be asymptotically stable? What that means is, is that stable enough in this notion of Lyapunov stability, which we haven't defined, we'll show. But loosely speaking, if it starts close, will remain close, right? And and it has to converge for asymptotic stability. So if I actually draw a line, okay, so let's say this is the origin. If I start close, let's say somewhere here, because every point is an equilibrium point, it will remain there. So I remain close. So certainly it satisfies this loose notion of start close and remain close. Is it asymptotic? Certainly not, because you have multiple equilibrium point, and wherever you start in any of the other equilibrium point, you will never get back, right? So this is an example where we have just Lyapunov stability and no asymptotic stability. But on the other hand, if you have instead, right, instead x dot is equal to minus x, okay, so doesn't take much time. Basically we can see that x of t is e raised to minus t x 0, whatever the x0 may be, whatever the initial condition. Now, so the basically let's say you start close to it, you can clearly see it keeps getting back to the equilibrium point, or getting to the close to the equilibrium point, so it will remain close to the equilibrium point. So certainly it satisfies the notion of Lyapunov stability, and it also satisfies the notion of asymptotic convergence, so which basically means both the notions are true, and therefore this particular system is asymptotically stable, right? And you see that I'm using the word system. So basically when I say something like that, typically what I mean by that is, for every initial condition, the system seems to be going back to the equilibrium point. Under very restrictive cases, there's no distinction between the system versus an equilibrium point, but in most cases there will be a difference. So that's why we are going to be very strict in terms of calling an equilibrium point stable rather than the system. But in cases where we call system stable, we typically mean that there's one single equilibrium point, and then asymptotic stability is the notion, right? What else? Now this particular convergence is not only asymptotic, in the sense that it's not going to just reach the equilibrium point, but actually it reaches in negative exponential time, right? So, and therefore we can call that notion as exponential convergence, and basically there is certain measure to it, certain metric to it in terms of how fast it is converging, and that notion we call as exponential stability convergence. And if you have stability, then you will have stability. Yeah, it turns out basically if you have exponential convergence, then it will automatically imply stability. That's a different issue. But you have these, unlike asymptotic convergence, you can have asymptotic convergence without having Lyapunov stability, but exponential convergence cannot happen without Lyapunov stability. So these are the general notions. The Lyapunov stable, loosely speaking, start close, remain close. And then the second notion is asymptotic stability, which is combining Lyapunov stability and asymptotic convergence. And then third notion is exponential stability, which is slightly more than asymptotic stability, which not only says you have asymptotic convergence, but actually certain rate of convergence, right? So these are the three notions, and let's have a discussion on Lyapunov stability for the time being, and then go to look at the rigorous definitions. Now, how do we define start close and remain close? The words things like close and things like that are quite ambiguous. So unfortunately or fortunately, we need to quantify them, and then ever since introduction of continuity, rigorous continuity results by people like Weierstrass and Cantor and others, the so-called epsilon delta definitions have come into picture, and many people they become inherent block in terms of understanding. But hopefully we will see what we mean by Lyapunov stability, right? So start close, remain close. There are multiple ways of thinking about it, but there is a specific way that makes sense. Every other way, if you actually start writing it, it does not make sense. And I'm not going to try to convince you it does not make sense, but at least this one makes sense, right? So given an epsilon, okay, let's say we are thinking of an equilibrium point in two-dimensional space, and I'm going to construct a ball of let's say radius epsilon. So this equilibrium point has a ball around the equilibrium point of radius epsilon, right? So given some epsilon, what do I want? I want to find out all the set of those initial conditions, right, including the origin. If I start within that point, I'll remain in this ball, right? So in other words, I am actually looking for a smaller ball, okay, obviously, because if I have a bigger ball, then basically I won't, I mean, it'll take for some time. Even if you have some kind of convergence, it'll take some time. So I will never remain within the proximity of the equilibrium point. So I'm looking for a smaller ball, perhaps of measure radius delta, such that wherever I start within this, I will remain in epsilon, right? Sometimes I may even just go directly to the equilibrium point, never stepping out of my delta ball, right? So all those things are possible. So, and then this has to happen for every epsilon. So even if obviously if I pick bigger epsilon than this, then the same delta ball will work for me. So if I actually keep reducing my epsilon, right, however small my epsilon is, I can still find a smaller delta, and if I start the initial conditions there, I'll remain in that delta epsilon, right? Again, I want you to understand that this notion works very well by, if you think basically, if I keep reducing my epsilon, still I am going to find a smaller ball, and in those initial conditions, if I start, I remain within that epsilon, and that is basically what Lyapunov defined as stability, and which we today call as Lyapunov stability of an equilibrium point, right? Now, one of the questions that we can ask ourselves is, suppose we have a case where an equilibrium point is asymptotically convergent. let's say, globally asymptotically convergent. What that means is anywhere in the space you start, you go back to the equilibrium point. So then what is the point of having a notion of Lyapunov stability, right? So not only we want to get back to the equilibrium point, we want to do it optimally, right? I mean, there's no real optimality defined here. There is no objective function or anything like that described, but we don't want our system to wander off somewhere and then come back after a long time and things like that. So this Lyapunov stability notion actually enforces certain well-definedness of this particular behavior, right? Now, so if you start close, you will remain close. And in fact, however close you want to remain, which is what is defined by epsilon, okay, you can find a set of initial conditions that will ensure that you remain that close to that. So, the actual notion of Lyapunov stability is, if I want to remain close within a certain level, how far can I go from the equilibrium point without breaking the rule of remaining within this particular epsilon. So I want to remain in epsilon. What is the biggest delta? The smaller ball, right? So let's say this is epsilon ball and this is delta ball. How big can I find this delta? I mean, we don't really care to find the largest necessarily delta, but can we find a delta is usually the definition of Lyapunov stability. But how large can this delta be before we go out of this epsilon ball, right? So that closely explains, or very rigorously explains, the notion of start close, remain close. But in reality, what we are trying to say is, you want to remain in close proximity that has a measure of epsilon. This is a quantifying definition. How far can I get from the equilibrium point? So that is defined by delta. So rest of it is actually fairly straightforward. Basically, once we understand the notion of Lyapunov stability, asymptotic convergence, if you add to it, then basically it becomes asymptotic stability. And if further we have some kind of rate of convergence that's given by exponential decay function, then basically we can call that exponentially stable. So all these notions, let's provide a rigorous definition. So given an ordinary differential equation of the form x dot is equal to f, to start with, we will assume that the 0 is an equilibrium point. Like I said earlier, basically, even if the origin is not the original equilibrium point, you can shift all the coordinates so that the origin becomes the equilibrium point. Anyway, so here we assume that f of 0 is equal to 0, so that the 0 solution is an equilibrium point. So then the rigorous definition of Lyapunov stability goes something like this. The 0 solution is Lyapunov stable if for every epsilon there exists a delta such that if the initial condition is within this delta, then the solution will remain within epsilon from a norm upper bound perspective, right? And the 0 solution is asymptotically stable. I put this word locally in parenthesis because whenever somebody uses the notion of asymptotic stability, they obviously mean local, but to emphasize, I put that word there. So this 0 solution is locally asymptotically stable, or simply asymptotically stable if it is first Lyapunov stable. That's a basic requirement. Like I said, we don't want our solutions to just wander off. And there exists some ball around the origin. This delta could be very different from the deltas we are talking about for Lyapunov stability, such that this solution goes to approaches 0, right, for all the initial conditions within that ball. So if you are trying to solve some particular problem and understand what is going on, you will have a delta ball around which basically if you start there, you will get to the 0 point, and there could be some other delta that will enforce some kind of bound in terms of epsilon. You may pick that epsilon. So pick the smaller of these two deltas, and then it will work both in terms of basically ensuring you remain in epsilon and also the convergence happens, right? So in a practical sense, that's how one can solve problems involving asymptotic stability. And further, if this convergence happens in a certain manner, specifically the norm of the x of t is less than or equal to some positive constant alpha times the initial condition times exponential decay function like e power minus beta t, where beta is positive, then we call that as exponential stability, right? Now, I do say that this has to be Lyapunov stable, but actually this condition itself will ensure Lyapunov stability. So that in that sense, I never had to say it's Lyapunov stable. So one can easily see that as t tends to infinity, the right hand side of this inequality goes to 0. So therefore, the limit of x of t is going to 0. So every exponentially stable equilibrium point is automatically asymptotically stable equilibrium point. Okay. So, moving forward, these are all the local definitions, and then you have the global counterparts, which straightforward, there are no epsilons and deltas. Zero solution is globally asymptotically stable if it is Lyapunov stable. Of course, the hidden epsilon deltas there in the definition of Lyapunov stability. But for every initial condition, my solution converges to 0 anywhere in the space of Rn, right? And the global exponential stability, like I keep saying, basically it provides all the nice things, all the good things. There's one single inequality that ensures Lyapunov stability as well as asymptotic convergence with a particular rate, right? So these are the definitions that Lyapunov gave us, and then in his honor we call the basic notion as Lyapunov stability, and the more restrictive converging notions as exponential and asymptotic stability, right? So now let's look at the definitions and understand how can one check for Lyapunov stability, right? I mean, beyond the confusion in terms of what are these epsilons and deltas, but one thing that is obvious from any of these definitions, not just Lyapunov stability, is one has to check that each of these conditions, given a ball of delta, we should be able to check for every initial condition within that ball, it's going to be less than epsilon for all time. So multiple things are happening. So first thing is basically for every initial condition, we should be able to figure out a solution, and then every solution is going to be remaining this epsilon after magically finding these epsilons and deltas. So in that sense, even numerically, I mean, if you do it blindly using numerics, you always have the nagging feeling that basically there may be some initial condition where this may not be true. This may be missed, and some of our numerical methods are so approximate sometimes they don't capture. We have seen in earlier discussions that basically certain fundamental aspects of knowing that a solution exists or unique is necessary in terms of using numerical methods confidently. In the absence of that, then basically things get really problematic. And then how does one check for stability? Absolutely no way. I mean, the only case that we can think of where this can be seen is actually linear, and we'll look at that in the next lecture. So one can actually find solutions for linear systems. Therefore, we can show a lot of these things in a relatively straightforward manner for linear systems. But for nonlinear systems, what's the approach? Well, that is where the power of Lyapunov's contribution comes into picture. He not only defined all these notions, he actually provided nice theorems, to show, to prove all these notions, right? All the 5 notions that are in front of us, right? So that will be the next lecture, but let me just basically go through some generalization. So like I said, in many examples, including orbital mechanics, you may have periodic orbits, like our Earth goes around Sun in a certain amount of time and things like that. So therefore we want to talk about stability of such motions rather than a single equilibrium point. And so you can generalize this Lyapunov stability notion to such orbits, and essentially if you perturb basically from the orbit, will you get back to the orbit? That's the asymptotic convergence part of it. Lyapunov stability aspect of it is, will you remain close to the orbit, right? And there are subtle differences whether you remain close to the orbit, and perhaps you are on the other side of the orbit, and so on. So there are notions of stability of sets, specifically stability of invariant sets, like equilibrium, if you start there and you remain within that equilibrium, and we built stability around equilibrium points. So the generalization of that to sets is something to do with invariant sets, periodic orbits or such sets, right? So if you start close to the set but out of the set, will you remain close to the invariant set? That's the notion of Lyapunov stability of invariant sets. And then getting back to the set is the asymptotic. Both combined together, you will have asymptotic stability of sets. And the more general notion is something to do with time varying systems, and because you have a third parameter, not just initial condition and the system, basically you also have the time initial condition, and that makes things much more complicated. And then you'll have notions, whether this notion of stability is uniform with respect to time and things like that. These epsilons and deltas that we are talking about not only may depend on the initial condition, but actually may depend on time and things like that, right? So you have these, and then stability of time varying systems can be quite complicated. And earlier, like I said, stability of time varying systems can be converted, rather time varying systems can be converted into time invariant systems. Unfortunately, one of the variables will not even have an equilibrium point, and that will lead us to even more interesting notions of stability of partial equilibria, right? I won't get into some of those things at all here, but completely another counterpart to these notions is stability of stochastic systems, where everything is kind of random, and even the equilibrium may not be an equilibrium in the traditional sense. And so how do we define stability for such systems, right? So do we have results for Lyapunov stability or things like that in stochastic systems? The answer is yes. I mean, there are many generalizations, but things get really complicated, and the math gets really weird and things like that. So I already spoke about this partial equilibrium. We can have parallels between time varying systems and partial stability and things like that. And there are other notions that I don't necessarily consider. Maybe some example here and there I may show you. There's a very interesting concept called semi-stability. This is somewhere between Lyapunov stability and asymptotic stability. So for every solution that starts close to the equilibrium point, it remains close, but if it it may go out, but it actually converges to some particular point, right? Not the equilibrium point that we are trying to check the stability of, but it may reach some other equilibrium point. It has the property of staying start close, remain close. So that means you will have a bunch of points close to the equilibrium point, but as time goes to infinity, it may converge to some other equilibrium point that is actually close to the equilibrium point in question, and that notion is covered in semi-stability. Again, you can think of convergence again without convergence to a alternate equilibrium point without the notion of Lyapunov stability, and that may be of interest independently from stability, but both combined together is what we call as semi-stability. So that's sort of an introduction to the notions of stability, and we will see how one can check, like I said, the complexity of checking for stability using the definitions the way we have is, numerically it's impossible because we can never cover all the initial conditions and time and things like that. And if you don't have a solution, then you don't seem to have any way of moving forward, and then that's why we celebrate Lyapunov for his results, and that's going to be the focus of the next lecture. Thank you.